So this is hopefully a fun talk. This is a talk I gave this weekend at a local tech event called Minnebar, which I don't know if you can read the logo. It's Minnesota Tech Design and Drinks. We geek out and drink beer. And the subject is never trust any published algorithm. And I really mean never. But why should you care? New algorithms are invented all the time. Some of them may actually be useful. I'll show you some examples that I hope are useful. Sorry, I didn't introduce myself. I'm Mark Gooder. If I haven't met you guys, I'm one of the co-founders of the company. Correct implementation of algorithms matters a lot. Correctness translates into quality. It's not the same thing, but if the algorithm is not correct, the quality of the product that uses it is going to be low. And the techniques which find bugs in algorithms that I'll give you some examples of are widely applicable. And some of these techniques we even have used at Tintri. So let's start out with an algorithm I recently implemented and got very frustrated with. So it's an algorithm for analyzing log message types. So what does this mean? We have a set of log output from a Tintri box. We want to heuristically partitions the log into messages of the same type and recovers the original definition of the event. So we do a pretty good job in our support log of putting a label on everything, but debug log is just whatever. So can we from a debug log actually recover what were the formatted statements that generated the log message? And this is a pretty useful thing to do. So I actually talked to Alexandra about this, and he had some suggestions, and I thought about how I might do it, and I said, okay, somebody's probably solved this. So I found a paper. The guy had been published in peer-reviewed conferences and journals multiple times, so great. This must be a good algorithm to use. That was not my experience. The algorithm was underspecified. It had what I consider to be obvious errors, and his source code download was a 404, so I couldn't even tell what he had thought he was doing. So here's one of the heuristic steps. We're looking at two columns in the text, so two positions within log messages, and one of them we think is a constant, and the other one we think is a variable, right? That for example, in this example, we might be looking at link and down or up, and link is a constant and down or up is a variable. That's what we're trying to find in this particular heuristic. And he says, okay, we're going to calculate a metric which he calls distance, and we're going to map it. We're either going to, on the lower bound, we're going to treat it toward being a variable, and on the upper bound, we're going to treat it as being a constant. And in the middle, who knows what. Okay, so there's his code from the paper. Can anybody here find what the error is? All right, so his picture, and this picture appears in multiple versions of the paper, has three sections: below the lower bound, between the lower and middle bound, above the upper bound. And there are three cases in the code covering that. And in case one, you do something. In case two, you do something else. And in case three, you do exactly the same thing as in case two, right? So the upper bound has no effect whatsoever on the implementation of the algorithm. It's just a totally extraneous parameter that he put in, and it doesn't do anything. According to what he described in the paper, it doesn't do anything. Okay, so you see that in the code? All right, so how did this happen? If you have a parameter and you describe your algorithm in terms of 4 parameters, and one of the parameters doesn't do anything at all, shouldn't somebody have noticed? Okay, the bad news, and this is a general point about published algorithms, is they are likely implemented only at most once by one person, right? there's no code review. There's, the peer review does not include code. The reviewers and shepherds are busy. They have their own priorities, and they certainly don't try to write their own implementation of the algorithm. So things that sort of look okay on the surface, but when you take a deeper look, make no sense. They don't get caught by this process. Right, and maybe the code used in the experiment does something sensible, or maybe it doesn't. Like I said, I can't tell. But this is typical of published algorithms. You really got to ask yourself, has this ever been implemented successfully by anybody other than the original author? And you really want to be the number 2 person to try to implement the algorithm based on a incomplete description of what was actually going on. So, what's our lesson for development? If only one person understands the algorithm, the odds are it doesn't work, or it's got some feature that doesn't work the way the person who wrote it thinks it does. So really, code review, have 2 people, maybe even go so far as to have 2 people prototype it to make sure that they really understand what the specification of the algorithm is. Most of the effort is in release hardening and maintenance and testing anyway. If you can just get 2 people to really think about what is going on in the algorithm, you've gone a long way from going from a algorithm that's probably not correct to an algorithm that's probably correct. Who do you think? No, the grad student is the person who's writing the algorithm once, right? These all this guy's papers. I haven't identified it by name because the point is not to shame him. The point is to make a point that this happens overnight. So all his papers were him and 2 of his professors. But guess who was doing all the work? All right. So this next example was a really big deal when I was in grad school. I don't know how many people actually remember Napster at this point, but Napster came out and got bazillions of users illegally sharing music with each other, and all of a sudden peer-to-peer became academically respectable because now there was a real-world example of people using peer-to-peer technologies. So there was a flood of research that came out, some of it rehashing older stuff that had been done on peer-to-peer technologies. And the best of the bunch really was this algorithm called Chord. So it uses peer-to-peer technology to build an ad hoc, scalable, robust key value store. So it's basically a big dictionary distributed across multiple machines, and machines can come and go, and the system still works in the presence of failures and joins and leaves. So this was an award-winning paper. It actually got an award in 2001 when it came out, and it got an award 10 years later, as this research has stood the test of time. The people who worked on it were very respected. I'm not going to spend a lot of time describing it, but basically every node who joins is assigned a number, generally based on an IP, a hash of its identifying information, its IP address, and maybe its port number. And all the nodes in Chord are arranged in a circle based on number, and then items are stored based on the node that has the number closest to them. So if I'm going to store key 80, it would go in 101. And the circle by itself is not enough. You need some shortcut information so you can actually find things in a reasonable fashion. And one of the mechanisms for recovery is that every node points at the node 2 along the circle, these blue arrows I've tried to show. So 55 knows who 79 is, and it also knows who 101 is. So if 79 goes away, it can undergo a recovery step. And so this paper actually has a proof of 7 things that they claim hold, and guess what? None of them are true. None of the things claimed in the paper about the algorithm they describe actually hold true of the system as described. So Pamela Zave, who's at AT&T Research, published this paper using lightweight modeling to understand Chord. So she actually, I'll talk about this in the next slide is what actually she did. But here's one of the examples for her paper. Here's a cord peer-to-peer network with 3 elements, and everything's consistent. The 3 members join and incorporated into the ring. So 5, 21, and 49 added, but the second hop links aren't updated atomically. So if those 3 nodes then fail, we're left with a ring where the elements are now out of order. So it goes 0, 40, 18 rather than 0, 18, 40. But you would advance 1 hop around the circle and find 40, and it would say, I don't have that. You need to look somewhere else. Right, so the very properties that are supposed to make it robust don't actually hold in a real world implementation. So she used a tool called Alloy, where you basically build a formal mathematical model of the system, and you check that the invariants that are supposed to hold actually do hold under a variety of operations. So the tool basically looks for counterexamples. It doesn't prove correctness. It looks for, here's a situation that fits everything you've described, but the invariant doesn't actually hold. So, one of the examples here is, a predicate that there's at least 1 ring and there's not 2, and the ring is globally ordered. So, it's a mathematical description of what is the protocol supposed to be doing. And I have used this. I'd be happy to give an example. I'm not sure whether we did a tech launch on it. This is a tool that's been around for a while. It's not new. So how did this happen? Informal reasoning about failure conditions. It's easier to focus on the examples work rather than really thinking hard about what are the examples that violate the assumptions I have made. It's easy to fool yourself when you're engaging in informal reasoning. One of the quotes from Dr. Zave's paper is, distributed systems frequently do not work the way we expect them to. So, and it's kind of strange because this is not a case of the first failure I showed you. People wrote follow-up papers. People made their own implementations. This is not an algorithm that was only implemented once. It's been implemented about 10 times. And what Dr. Zave found is none of the implementations concurrently defined which of the published versions they were actually implementing. And if they found any of these problems that her model checking found, those results never got pushed back into the broader world. Nobody gets paid for checking somebody's proof. I'll talk a little bit about that. But again, that's sort of a limitation of the peer review cycle is you don't know, your advisor is never going to encourage you to go check somebody else's proof and make sure it's still true. People working in formal verification can get published by, I have a new verification tool, I tried it out on a real world protocol, guess what, it didn't work. But that's the exception, not the rule. So, even though the tools were available, even in 2001, to do this sort of analysis of the distributed system under failure, nobody bothered to check for literally a decade. So, if you have a proof, that proof is only as good as the amount of checking it receives. I talked about there's really very little incentive to check a proof in any level of detail. Nobody gets published for saying, yes, I believe that proof is correct. It's a high risk endeavor. You can get published for proving it's wrong. You can't get published for saying, yes, it's true. So if correctness matters to you, you need to find a way to check your design. And there's more than one way to do that. There's coverage tools. Did all the branches of my algorithm actually get exercised by my tests? There's model checkers. Can I find a counterexample to the properties I think hold? There's fuzzers. Fuzzers are very neat. There could be a tech lunch all of its own. They're used to find bugs or exploits in parsing libraries, like image processing libraries or zip functions, by just making sure, testing that all different permutations of branches through the code get covered. There's some amazing things I'd like to play with there more. I've played with model checkers. I've played with coverage tools. I haven't done much with fuzzers yet, but they're very smart tools, and the hacker community is very motivated to make these better. Model checkers come from the academic community. Fuzzers come from the intrusion community. Okay. So as I said, the previous example, that was sort of my competition in grad school, and I lost. So I have sort of this schadenfreude of they didn't actually know what they were talking about. Not that my algorithms were necessarily better, but I have a personal connection with this one too. So one of the senior grad students when I entered Stanford was working on non-blocking synchronization. So I learned a lot about this from him. So non-blocking synchronization uses atomic processor functions like compare and swap, or in this case, double compare and swap, to implement a data structure that in a lock-free fashion. So the typical algorithm for a lock-free operation looks something like, set up some state, try to do an atomic operation to make it all right. If that operation fails, go back and try again, and eventually you'll succeed. So the Snark algorithm uses double compare and swap to implement a lock-free double-ended queue, a deck, where you can push or pop from either end. And this was published by a bunch of smart people, including Guy Steele, so people from Java and from, I believe, University of Washington. And if you can't trust Guy Steele on concurrency, how can you who can you trust? It includes a sketch proof of correctness based on with 7 lemmas and 5 theorems. So they really did their homework. The basic idea is it's a doubly linked list. You've got a left hat, which is your left end. You got a right hat, which is your right end, and you've got a couple of guard objects on either side, so you can do some of the non-blocking things in a memory safe way. So what breaks? 2 things break. One, an element can remove twice, and the second is the pop can fail when the deck is never empty during its run. So the basic properties of a double-ended queue of pop, if either of these happened, you would say, aha, there's a concurrency problem. So there's the code for pop right. It's pretty simple. It grabs the right hat and the left hat. It says if the right hat points at itself, it's empty. That's what an empty deck looks like. If they're the same, then I do one double compare and swap to empty the queue. Otherwise, I remove an item from the list. So I'm not gonna make you debug this one. But what happens is the first thread starts a pop right while the queue is not empty. It loads right hat. So this picture here, it says, okay, RH, my thread local variable equals right hat, the global variable. Thread A then gets delayed or descheduled, and other processes push something onto the right-hand side and then pop the element that thread A is pointing to off the deck. So this is a case that should have to happen. But notice at no point during that sequence did the queue actually empty out. So thread A resumes. It's now in this world. It says, oh, the element I'm looking at points to itself. That's the empty condition. I report empty. Okay. So this is not actually a very complicated example. I'll talk about that, but it's an interleaving of 3 different operations. It's not I had to set up 10 preconditions and interleave. It's I had to pause the thread in the right spot, do the right 2 operations, and I got a failure condition. So how was the problem found? Again, this was model checking. And so the original authors and a few more had to come back 3 years later and say, actually, that algorithm we proved was correct, not actually correct. And they used a system called PVS, which I haven't used. So again, if there's a proof, that proof needs to have a way to be checked. Otherwise, you cannot believe the proof. And if you can't believe the proof, you should not trust the algorithm. That doesn't mean you shouldn't use the algorithm. I'm not trying to induce NIMBYism. I'm trying to induce paranoia. If you believe something's correct, how do you tell that it's correct? And at this point, I would say if you've gone to the effort of writing a proof, you should develop a formal model as well that can be checked. It is not harder to make the formal model than it is to write a proof. And heuristically, most bugs have small examples. Like I said, just 3 operations in this case. It did not require a lot of depth to find this. So can you do exhaustive testing instead of a proof? Could you demonstrate that any interleaving of 3 operations is always correct? That would be a big step forward in correctness. And again, most bugs have small examples. So if there's a small amount of code and you really want to be sure, can you do exhaustive testing to make really sure? Even experts in concurrency get it wrong. These guys, their job is to do concurrent programming. and they were badly mistaken at what they had actually built. One of the things we have done from a software engineering point is using delay points to get better coverage during stress testing to really exercise different interleavings of code within the critical section. It's hard so the question was, why didn't anybody who was using this in production actually find it? Okay, so the dirty secret here is no modern processor has a double compare and swap operation. So the best you can do is simulate it using a lock that's held only for a very small amount of time. So it is unlikely anybody put this into production. They implemented it, they tested it, they actually showed some stats of running it, but it is unlikely it got put into production. And the other thing is it's hard to diagnose after the fact, right? That if the queue is sometime allowed to be empty and your pop function occasionally turns empty when it shouldn't, that's very hard to go back and diagnose. Yeah, so the Motorola 68000 has a double compare and swap, but no other architecture I know has one. And so the point Michael Greenwald, what Michael Greenwald, my friend at Stanford, proved is that double compare and swap is universal for non-blocking operations, and that's why there's some interest in it. Is because if you have DCAST, then you can build any non-blocking data structure you want out of it. They did not in their original paper say, and we ran stress tests on it. So it's again, what can you do to increase your confidence? Arguably, all of those are very theoretical examples, right? The first algorithm was practical, but I managed to make it work anyway. These last two, it's really never gotten in the field. It's not like it's affecting millions of people. Okay, I'll show you an example that, while it doesn't affect millions of people, it is in code that millions of people actually run. Okay, so there's a sort called timsort, which is a combination of merge sort and insertion sort. It tries to take advantage of is it frequently comes with sorted subsequences already in it. It's unlikely somebody does a random shuffle before handing the data to sort. If you're pulling it out of a database or you're doing a web query, probably some subset of it may already be sorted. So timsort finds existing runs that are already sorted within the array, subsequences that are already in increasing order by their key. And if the run's not long enough, then let's use insertion sort to extend it. And insertion sort is very bad from a sorting big arrays, but it's actually very good for sorting small arrays. So it's okay as long as you're not using it over the whole array to just make a, if you've got 10 elements, then let's extend that to 12 elements. That works fine. And then we merge pairs of runs during the sort and a final merge over all the runs at the end. And as William knows from asking this question in coding interviews, merging two sorted sequences is very fast. You can do that in a linear time. So what this requires is an auxiliary data structure that's used to track the length of the runs. And that auxiliary data structure is where problems come in. So this is Python sort function. It was developed for Python in 2002, and it got ported to Java. And Java util collection sort is this algorithm. So the claimed invariant is that the run lengths grow faster than the Fibonacci sequence. So if you've got a run length, the sum of the two run lengths is the run length is greater than the sum of the two run lengths to its right, and let me just show. So the invariant is that this is greater than the sum of this, and that they're all in increasing order. So this is the invariant we need across all run lengths in our array. And what was claimed is that we only need to check this at the end of the array in order to verify that it's true for the whole array, right? So we look at the very end of our run lengths and we say, okay, is the first invariant a problem? If so, we'll merge it and we'll look again. Otherwise, if the last two are out of order, then I'll merge them and look again. Otherwise, the invariant holds. Okay. So this is not actually true, which should be no surprise at this point. That the claimed property does not actually hold. So the counterexample that the people who found is here. So we've got an array, and the invariant is broken right here. 30 is bigger than 20. So we want to merge these two. We want to merge. The algorithm actually chooses to merge those two, and it ends up in a situation where the invariant's verified here. The invariant doesn't hold here. 80 plus 45 is bigger than 120. And what this means is that more slots are used in this run length array than the algorithm predict. So the size that we need to allocate for the run length array is not big enough. It doesn't mean we didn't sort things in correct order, but what you do get is an out of bounds exception. So you can actually go download their code, run it, and Java will throw an out of bounds exception from its sort. So how did they find this? They were attempting to, again, like I talked about, you can get published for using your new tool to prove that existing algorithms are correct. So they had a new tool. They proved that Java's counting sort was correct. They proved that Java's radix sort was correct. They went on to the Tim sort implementation and could not prove that it was correct. And so they sort of scratched their heads and were able to generate a counterexample that showed that it was not in fact correct. And the way their tool works is it annotates codes with preconditions and postconditions, and then an interactive theorem prover shows that those preconditions, postconditions, invariants are true. So it's not purely automated. You have to give it some hints, but you can't lie to the automated theorem prover. That's what it gives you is whatever you claim is true. It will say, can I show that or not? So what happened in this case, the authors submitted bug reports to both Python and Java. And Python did the right thing. Python put in the extra check that they recommended, which actually does preserve the invariant, even though Python didn't actually have this problem in practice. The counterexample would already have been too large to fit in any feasible machine's memory, because they sort of put some extra space in the run length array anyway. And somebody asked in the bug report, is this extra check really worth it in terms of runtime? We're never really going to run into this. Can we just pretend that it doesn't occur? And the original author, Tim, I don't know what Tim's name is, but the author of Tim, sorry, said, the number of times this procedure is run is logarithmic in input size. It's far better to do the right thing and not store up trouble for ourselves than, just sort of weasel word around the problem. Java took the weasel way out and they just bumped the run length array. So there is a patch coming in Java that will fix this, but it's not the right fix. The algorithm is still not provably correct. So automation tools are really viewed as research and not ready for prime time, and this has been true for decades, and I think it's not as true as it used to be. The authors sort of issue this challenge that says, yeah, it takes work, but it's like learning a new programming language, not like going back and getting a PhD. So what's the excuse? And the other, thing which should be obvious but is not always obvious is just because millions of people use your algorithm doesn't mean it's actually safe. Particularly not safe when you use it in a different way than those millions of people use it. Very few people sort 67 million element arrays, and that's how big the counterexample was. So, what do you think? Most errors are a lot more basic than this. I think there's a good attitude to say, look, the average level of skill in the software development community is so low, we need to solve that problem first. If you have never read the Daily WTF, I encourage you to do so, to see what sort of things go into real world systems that really cannot be explained. So if we can't even get simple tasks right, why worry about the complicated tasks? The other point I make is engineering is about trade-offs. Correctness is not always the top priority. Product quality is the top priority for us, but ultimately we are paid because our customers give us money, not because the customers verify that our theorems are correct. So do you have any examples you'd like to share about broken algorithms or using formal methods? Brandon's not here. We could talk about some of the stuff we've done with our controller election mechanism to attempt to verify that. What do you think? Are you scared? Amused? Paranoid? Amused? Okay. Well, I've got two more amusing examples. Is this the Sivir of Eratosthenes? So who knows what the Sivir of Eratosthenes is? You people, okay. It's a method for finding prime numbers, and this code is Haskell. How many people know Haskell? Wow, that's much more than I thought. All right, so I should get you to explain it, because I can read Haskell, I can't write it. But this says, okay, to find the prime numbers, we sieve all the numbers from 2 to infinity. And the way we sieve is we take the first element of the list and the rest of the element. First is P, rest of the list is XS. And the first thing on our list is a prime. And then we recursively call sieve with anything not divisible by the number we found as a prime. So we run through our list and in a lazy fashion, check whether anything is divisible by 2, and then whether it's divisible by 3, and whether it's divisible by 5, and divisible by 7. So that's correct, but it's not the sieve of Eratosthenes. The sieve operates in the other way. It marks off all composite numbers, and it finds the first number that's not composite and marks off all multiples of that. So the first clue is that the sieve of Eratosthenes only does multiplication, never division, and this guy is doing division. This is actually trial division, and yet 30 years of functional programming papers have claimed a benefit that, look how easy it is to implement the sieve of Eratosthenes. I can do it in 2 lines of my favorite programming language. And that's not what this is. So you should check this paper out. It's very accessible. It's very fun. It's amusing the excuses people made about, oh, well, garbage collection is slowing us down. No. You're using an algorithm that's got a completely different runtime than the one you said you were implementing. So, this is a step, you need to be sure you're actually implementing the algorithm you think you are implementing. All right, and for Alexandra, I've got a big data example too. Clustering of time series subsequences is meaningless. So this is a data mining technique where you chop up your time series data with a sliding window, and you run a clustering algorithm on all those slices looking for meaningful data. And this was introduced in the early 2000s, and there were about 25 papers using this technique after it was introduced, and the technique does nothing whatsoever. It has no value. It's not even garbage in, garbage out. It's anything in, garbage out. So, you know, I found this the night before my presentation, or I probably would have promoted this, because this really has to be seen to believe that 25 different research groups said, this is a great technique. I'm going to go and find correlations in time series data, and their technique has no explanatory power at all. So don't trust published algorithms. That's not don't use them, but be sure you understand them, be sure you test them. And if you can check them, and it's worth checking them, find a way to check them.